So good afternoon, everybody. Today we are going to discuss, as I said, autoencoders, a very important type of neural network. I'm going to share my slides screen. Yeah. So now you can see that. I hope you can see my slides. Yeah, good afternoon, everybody. Can you see my slides? Please write yes on the chat box if you are able to. Yes, thank you. So welcome to day 8 of this program on machine learning for computer vision. I wish I could interact with you in connection with object detection and also convolutional neural network, but somehow we could not discuss. I was not able to present. So let's talk about first unsupervised learning before we go ahead with the problem of the concept of autoencoder. So as you can see that the algorithms, the networks that we have studied till now, these networks were all requesting you, I mean, they were expecting that we are having a label with each sample, right? So you have a sample X and a label Y, and then you were training the algorithm based on the sample and its corresponding label, right? Now, this type of learning by your algorithm is known as supervised machine learning, where we have labels. That means you have some prior knowledge of the training samples and you use that knowledge to train your network. That is the basic idea. Okay. Now, right now, we will be having another kind of neural network, which we are not training using the labels. This kind of learning is known as unsupervised learning. So there is a small difference between supervised and unsupervised. In supervised learning, you have data along with samples, and in unsupervised learning, you don't have labels or the prior knowledge about the data. So unsupervised learning, how we go with unsupervised learning, we discover intrinsic features of the data to obtain, to cluster them into subgroups, right? So you don't have, suppose you have, suppose it so happens that in a hospital, every day, some 200 to 300 X-rays are taken. Now the technician has no idea as to whether this X-ray is having some infection or pneumonia, or it is a normal chest X-ray, for example, right? So let us think about chest X-ray, and there are two different types of chest X-ray, one which is affected by pneumonia, the other which is normal. Now, technician will look into the features, will look into the visual features of the X-ray images and will try to put them in two categories or two groups, two subgroups to be precise, and that is what is known as understanding the intrinsic features of the data to obtain subgroups among the observed data. So data samples in a subgroups are expected to have greater similarity or degree of closeness than those they fall in different subgroups. So we will expect that all which are normal X-ray chest X-ray will fall into one group, and all which are abnormal chest X-ray will fall in another group. So I told you that X-ray images of COVID-19 patients, other pneumonia affected patients, and normal persons. So here they can be clustered into 3 different subgroups. Or you can think of customers characterized and grouped by their browsing history or purchase history. You can accordingly characterize them. You must have seen that while organizing your photo files in your albums, often you come across your images which are containing road scenes, images which are selfies, images which are group photo of your family, your friends, or they can be natural scenes. You must have seen that Google identifies them and clusters them into different subgroups. This all comes under unsupervised learning. So why do we need unsupervised learning? Because most of the data, my dear friends, is unlabeled, and the contents of the data may not be known. It may help gain some insight into data characteristic, but you may not be very much clear about whether this data is, like in case of supervised learning, we definitely know that this data belongs to class A, class B, category A, category B, category C. This information is missing. So every day you are taking certain pictures. I just told you that every day technician is taking so many X-rays. All these are unlabeled data, right? So why do we need supervised learning? Because we need to analyze that data, which is mostly unlabeled. For example, news. You keep getting several news items on your WhatsApp. Whether that is fake or authentic, you really have no idea. Similarly, sentiments expressed through messages on Twitter account, whether they are negative expressions, provocative, or neutral. In the present context, this has become very important area of research. Similarly, similar image retrieval from a large set of images. All these are basically problems that require machinery that doesn't need any labels on the data. So for data labeling, human intervention is needed, which is very highly time consuming, costly, and is prone to errors as well. So neural networks for unsupervised learning. Let us begin with one instance, that is autoencoder. A basic autoencoder is what? It's a neural network. And how it is trained? It is trained to reproduce its input. That was the very first autoencoder that was introduced and was very extensive, is still being used very extensively. So a basic autoencoder is nothing but a neural network that is trained to reproduce its input. If you have not understood, don't worry, I'm going to explain to you. What is the main objective? Objective is to capture the features of its input in a code that can be used to exactly reproduce the original input. So what we do, we have an image, right? You have an image here. This is an image X. I encode this image into a vector, we call it a latent vector, say Z, right? And then when I decode this vector, which is a latent vector, I get back another image. X is the original image. X hat is the reproduced image. Autoencoder tries to exactly produce X. In other words, autoencoder produces images X hat whose distances from X are very close, right? This is very close. So minimize the distance between X and X hat is the basic objective of an autoencoder network. Is that clear to you? If yes, please write yes on the chat box so that I can see whether you have understood this or not. Okay, thank you. Thank you. Many of you are able to write. If there's anybody who has not understood, please tell me. So you can see that X is an input. Fx is the function which is encoding it. F is the function which is encoding X. And what is that function? That is realized through this encoder network. That is, here is a neural network, which is an encoder network, which will encode this into Z. Z will be again try to decode, it will try to decode, G will try to decode Z so that you get another vector. And this vector should be as close as possible to X. That is the idea. So the aim of the autoencoder is to learn a representation for a data set. So given a data set, it tries to learn the representation. I hope you remember when we discussed about machine learning, deep learning. I told you that representation learning is a branch of machine learning, and deep learning is a special type of representation learning. So here, the aim of the autoencoder is to learn the representation of the data. It learns the representation of the data. Typically, that was for dimensionality reduction, but not always true. So when a neural network is trained to learn data representation, it ignores noise present in the data sample. That is very important of convolutional neural network or neural network, that they tend to ignore the noise present in the data samples. So along with dimensionality reduction, the neural network also learns to generate the data from its encoded vector Z. This is the reason we call it autoencoder. I hope this is clear to you. So let's see. You have a network, okay? You have a network, X1, X2. X6 is the input to the this layer, which is a hidden layer. You have this as an input layer. And +1 we have written here just to indicate bias. So suppose here you have got 3 neurons and you have got 6 input vector of size 6. So I will be writing, X1, all these X1, X2, Xn will be having their own, they will be interpreted by this neuron through their own weights, right? So the first neuron will be having, say, W11 X1 plus W12 X2 plus W16 X6 plus this +1 plus B1. I hope you know that this is what Dr. Rai also told you, that this is how it will be done. This is 1 here present because I'm talking about the first neuron. Similarly, for the second neuron, W21, X1, W22, X2 plus W26, X6 plus B2, okay? And similarly for the third. So you get the output here from the hidden layer coming as the input to the, output of the first input layer coming to the hidden layer as the input, and input layer will be interpreting, each neuron in the input layer will be interpreting them using their own weights and biases. So that is the idea. All right, so then after this, we will be applying the activation function. And activation function on this will be applied, say J varying from 1 to 6, W 1J Xj. On this, I will be applying an activation function, whatever activation function. And similarly, for I will be applying activation function on the second neuron's interpretation, that is W to this xj sigma. If suppose I use sigma, and the third sigma is the activation function, suppose j varying from 1 to 6, W3j, xj, right? So these are three neurons. They will be interpreting the data input, and then an activation function will be applied. This activation function, when applied, gives you the value z. Z becomes the latent variable, right? So G becomes the latent variable. Now this Z, now you can see that whatever is this, sigma applied on this will give me Z1, Z2, and Z3. Agreed? So this Z1, Z2, Z3 goes to the decoder part. So, or you can say that it is basically a layer L3, which is the output layer in this case. And so this output layer will be decoding this Z1, Z2, Z3. So Z1, Z2, Z3 is encoded vector of X1, X2, X6, and X1 hat, X2 hat until this X6 hat. This is the decoded vector of Z. That is how this neural network called autoencoder works. You can see that there is no role of the label on the data set. There is no role, right? It's only reconstructing. So given X, I seek your attention, please. Given data X, objective is to learn the function F, encoder, and the decoder function G, such that F of X, which is the activation function S applied on WEX plus BE is equal to Z, and GZ, which is equal to S, that is again activation function on WDZ plus BD is equal to X hat. What is WE? WE is the encoder network's weight matrix, and similarly BE is the encoder network's bias parameters. And similarly, WD will be for decoder and BD will be decoder. So idea is to learn the functions F and G. Why? Such that HX, which is equal to G of F of X, should be able to give me X hat, and X hat should be very close to X. That is, X hat should approximate X. The approximate X means the distance between HX and X is minimized. So here H is an approximation of the identity function, because we are expecting H to reconstruct the original input. And that is why this is an approximation of the identity function. I give you some examples here. This is an example of a chest X-ray, right? You have a chest X-ray, and original image is this. Once it is passed through a neural network, you get a latent representation or latent vector, which is in this case, it's a latent array. And then this latent representation is fed to the decoder network, and you get the reconstructed image. You can see that this image that we are getting is quite close to the original image. So the idea of the autoencoder is to get your network trained in such a way that the input and the output vectors, or input and the output samples, for any input sample, the output of the sample should exactly be the same as the original sample. That is the idea. Okay. But people realized later that this is not the only reason why autoencoders could be used. There are plenty of other reasons when autoencoders can be used. Here is a plant leaf image. So this plant leaf original image is there. You pass through it a trained autoencoder, you get the reconstructed image. Similarly, for brain MRI, you have the input MRI image and you get the output image. There are various examples that you can construct. Let us take a numerical example. Let the input vector be x is equal to 1 minus 1, 0. I take a very simple example, right? Kumar Anjit is asking, what are the applications? You just saw some applications where it can be reconstructed, but we will come to the applications later. Please wait for a while. So let the encoder contain only one layer having 2 units, two neurons, all right? So let the encoder weight matrix and biases will be given by this. So you have got three-dimensional vector, you have got 2 neurons. So the weight matrix will be 3 cross true. This was asked in the examination. You have got bias vector here also, that will be of the size 3. So what will be W transpose X plus B? So you can see you can calculate what is W transpose X plus B by simply multiplying these matrices, find out, and then you will apply ReLU activation function to get the output so that you get the latent representation. So let the decoder weight matrix be like 2, 0, 0, 1, 0, 0. B will be equal to B is suppose this. Then you can calculate what is W transpose X plus B, and again apply ReLU and find out the error of reconstruction. Just here, let's take this example. This example. So I hope you will be able to do this quickly. So you have got 1 minus 1, 0, and this weight matrix. So I take the W transpose. So 1, 1 minus 1, 2, 0, 0 multiplied by, this is W transpose, 1 minus 1, 0. And then B is, I've taken purposely, for the sake of simplicity, I've taken that to be 0. So you get 0, right? And this is 2. Am I right? So you get 1, 1, 1 minus 1. When you multiply this by this, you get 1 minus 1, that is 0. And with the bottom line, if you, with the last line, if you do it, you get 2 and then 0 and then 0. So you get 0, 2. 0, 2 is the output from the encoder. So this is my X, this is my Z. And from the Z, what are you doing? You are finding out. Now you are given this, you have initialized your weight. So it is 2, 0, 0, 1, 0, sorry, I'm sorry. You should be taking its transpose. So it is 2, 0, 0 and 0, 1, 0. And then you will be multiplying this by 0, 2, right? To get the output. So when you multiply it by 0, 2, so you get, oh, sorry, I made a blunder here. Sorry, I wrote here the W transpose only. Give me a minute. So I get here this 2, 0, 0 and 0, 1, 0. So I get this is the W transpose, and 2, 0, 0, 1, 0, 0, and you will be multiplying this by 0, 2, right? So what do you get? You get 0, you get 2, you get 0. What was the original point? X was 1 minus 1, 0. So I have got 1 minus 1, 0, and you have 0, 2, 0. If I take the mean square error, so this will be 1 square plus, see here you have got -1, -2. So it is 3 square plus 0. So you get 10. So the mean square error, because we have taken only one sample, there is no mean that is required. The square error turns out to be 10. The idea is to minimize this error, my dear friends. While we are training our autoencoder, we will be, and I did not apply ReLU. Why? Because it is all non-negative values. So ReLU will give the same value. So let us come to the origin origin of the autoencoders, the idea. The idea of the autoencoder has been a part of the historical landscape of neural networks for decades, as is written in this book by Ian Goodfellow. But more recently, autoencoders are extensively used for a variety of different applications, including generative modeling, which Professor Prabir Vishwas and in GAN also, perhaps the other day, you must have studied about that. So what could be the applications of autoencoders? Somebody was asking. Somebody is saying that my voice is breaking. Are you not able to listen to me, friends? Hello, am I not audible?
Ma'am, it's clear. We can hear you properly.
Okay, but some people are saying, okay, some people are saying that my voice is not audible. All right, I'll share again. So what could be the applications of autoencoders? One application is immediately like representation learning, for which these were created. Dimensionality reduction. So what we do, we take a vector of size, say size 1024, we pass it through an autoencoder, right? And encoder part of autoencoder. So you can get a vector of size 256. That, and then this 256 is features are able to reproduce 1024. That means these are able to give you a good representation of the data, and they are also helping you reduce the dimension. Clustering. Now, because we don't have any labels, we don't need also any labels. What do? You take the encoded vector, that is latent space variable, and using the features of the data through latent space variable, you can apply clustering algorithms. Data compression, which is understood. The other applications include denoising, data augmentation, segmentation, and you will in this course you will study some such applications also. One of the very important applications is generative modeling. So generative modeling is a part of modeling where we are generating something, we are generating samples, we are generating, or we are learning the distribution of the data from where the samples are coming. So that is what is known as, so generative modeling means you are trying to understand what is the data, what is the probability distribution from where the data is coming. Now, so I come to training the autoencoder, my friends. The autoencoder is trained just like a conventional neural network. So don't worry about anything. It uses gradient descent. And to train an autoencoder for reconstructing the input, the loss function is taken as, for example, this can be one of the loss function. Like we expect that the distance between the original sample and its reconstructed image should be as close as small as possible. And so the idea is to minimize this quantity. norm of x minus x hat whole square. This is known as the squared norm, right? And if the input is a bit vector or a vector of bit probabilities, then cross entropy loss can also be used. For example, if you suppose you have changed your entire data into bits, right? Then in that case, what you can do is that you can make use of this cross entropy loss. Okay. There are two types of autoencoders. One is known as the undercomplete autoencoder, and the other is known as the overcomplete autoencoder. By undercomplete autoencoder, we mean that the original data is of higher dimension. Original data is of higher dimension. As you can see here, it reduces the dimension of the data, projects it to a lower dimensional space, and then it learns its representation of a data in terms of a lower dimensional space, and then it learns to reconstruct the data from this low dimensional vector. In case of overcomplete autoencoder, this will be the data is given. I have got the internal layers are such that they are now projecting. They are projecting the data into a higher dimensional space that is known as lifting, right? So I'm lifting the data, or I'm embedding the data in a higher dimensional space, and then from there I'm trying to reconstruct the given input vector, right? So these are two different types of autoencoders. So if I take this, for example, if the data comes from, say, MNIST data set, then these are handwritten images of handwritten digits. This goes to an encoder. You can see that this looks somewhat like this. This will be my encoder, like this will be my latent vector. Similarly, 9 is giving me Z2, which is also a latent space representation, right? So coming to convolutional, now autoencoders can be just like in terms of fully connected layers, or they can be like dense layers, as I said, or they can be convolutional autoencoders. Convolutional autoencoders are playing a very important role, and therefore we will be talking more on convolutional autoencoders. This here you have encoder part. You have an image. Suppose you have an RGB image. This is an image RGB. This is passed through a convolutional blocks, right? These are con blocks. And then you get a latent space representation of this input image. And from this latent space representation, you apply some deconvolving blocks, decoder block. And this decoder block will further try to reconstruct the original image. That is the basic idea of convolutional autoencoders. So it contains convolution and deconvolution blocks. And it may contain some pooling layers and some upsampling layers. Like basically deconvolution block is itself not exactly upsampling, but it increases the dimension of the input. Let us take this example of an image which is 6x6, this example is constructed by my student Nishant Khare. So I pass it through a convolution, 2D convolution with ReLU activation and same padding, right? Then I apply max pooling. Then I apply a conv2D again with ReLU function, and then I start upsampling, right? So let us take this example. Here I have got an image. Let us assume that these are pixel values of the image. I take the convolutional, these filters, 3x3 filter. So I apply a convolution here. Once when I apply, because I'm using same padding, my dear friends, the size of output will remain same. So when I apply this filter and convolve this filter with this image, I will be getting this image. I will not go into details. So that will be the convolution of this 2D output of the convolution, 2D convolution. Now, then I apply ReLU function on this. So you can see that these are positive, non-negative values, positive. This becomes -5, and therefore you have got a 0 here. Because ReLU is max of 0 and x. Similarly, this is -4, so you get a 0 here. Now, this is a ReLU function applied. So this is your activation map. This is my activation map. Okay. And from here, I will go to the max pooling layer. When I apply max pooling layer here, it's a 2x2 max pooling that he has applied to give you. If I take max pooling of this, you see that 11 is the largest number. Then I apply max pooling here. Then 16 is the largest number, which is present here. And then I apply max pooling again. So I get 20 is the largest number, which appears here. And so on and so forth. You can do it like this. And finally, you get the output after the max pooling. Now, on this max pooling, on this output, I again apply a convolution layer. When I apply a convolution layer, right, with the same padding, I get this matrix. I am not going into details of calculation. And then I upsample it using a specific method of upsampling, right? And that is here, we will see what are different methods. But here, what we are doing, this 56 1 pixel, I'm replacing by a 2x2 block in the next image. Similarly, this 78 pixel with value is replicated in a 2x2 block. And so this 3x3 becomes a 6x6 output. Is that clear to you? So this is the output image corresponding to the input image that I have chosen. I have done a simply upsampling operation instead of applying any other deconvolution operation. So the idea is to find out the error between, if suppose this is my x, if this is my x, oh my God, what's happening? So if this is my x, this is my x hat. And so the idea is to minimize the distance between x and x hat, right? That is the idea. Now, another example of convolution autoencoder, you can see that this is here, you can have as many convolutions here. And in this, they are applying. So it's a conv1, conv2, conv1, then max pooling. It downsizes the convolution operation output that you get from convolution operation. Then I conv2 and then max pooling 2, conv3, max pooling 3. And then I start deconvolution, deconvolution, decon1, decon2, decon3, and decon4. So you apply 4 convolution here. So you get apply 3 convolution here and 4 deconvolution operation. So input values are normalized. All of the conv layers activation functions are ReLU except for the last conv, which is a sigmoid function. When they apply this on a simple MNIST data set within only 50 epochs, you can see that they get good amount of accuracy, 88% accuracy on validation set with a good amount, a good quality of the output as well. So I use the term convolution layer. I seek your attention, please, to understand what is a deconvolution layer. Mathematical meaning of a deconv is basically inverse of a convolution operation. If the convolution on X produces Z, then the output of the deconvolution on Z should ideally produce X. However, in deep learning, deconvolution is not so popular. Rather, they apply transposed convolution or fractionally strided convolution for upsampling or upgrading the size of the given input. So let me define what is transposed convolution, which is loosely considered as deconvolution in many of the deep learning articles. You may get confused that they're using deconvolution, but they're applying transposed convolution. So let me tell you what is a transposed convolution, okay? 4321, 1432, 2143, 1234. This is suppose the input image, okay? This is my input image. This is the randomly selected convolution filter, okay? I will apply a convolution. When I apply a convolution, I will be getting -4, 4, -8, -4. So what I do, I apply 4 into 1, plus 3 into 0, plus 2 into -1, plus 1 into 2, plus 4 into 0, plus 3 into -2, right? Here, plus 2 into 1, plus 1 into 0, plus 4 into -1. When I calculate all this, I get -4. Similarly, when I apply this convolution on this part of the image, I get another number. And so this is the first number, that is -4. The second number is 4. The third number I get from here, that is -8. And the fourth number is -4. I hope this is clear to you. I'm applying a simple convolution. So after convolution, an input with 16 features, see, I seek your attention, please. And this is an input with 16 features, isn't it? You have got 4 × 4 number of features in an image. So these are 16 features. Is converted to an output with only 4 features. The question is, how can we get a vector of dimension 16 from an input vector of dimension 4? Mind you, I'm not saying how can we reconstruct the element. I'm saying how can we get a vector of dimension 16 from an input vector of dimension 4. So what do? I have got this. I apply convolution. When I apply convolution, I am applying it here. You can see that I'm overlapping this part. I'm overlapping this part on here, on this image. So I get it. You can see. And when I'm applying the convolution, you are actually ignoring this part of the image. You are only considering this 3 × 3 part of the image. Rest of it is given no weightage or 0 weightage. Therefore, what I will do, so you get this -4 you are getting because you are considering only this part, right? So when a filter is applied on an image block, contribution of other block values becomes 0, right? And then you can think of the filter size to be the same as that of the input image. I'm seeking your attention, please. Instead of this 3 × 3 filter, I will say that this is actually a 4 × 4 filter. This whole part is covered by the filter, except that Instead of a non-zero value here in this filter, which was non-zero value, I will say that, okay, this is 0, this is 0, this is 0. So even if I extend it to a complete, to the complete dimension of the input image, we are through. There's no problem because they are ultimately not going to play any role. So you have got 4, 3, 2, 1. You have got this. What I'll do, that I will be ignoring this part or will be applying 0, 0, 0 by, see what I'm doing. I'm putting this 4 cross 4 vector, 4 cross 4 vector as a 16 cross 1, sorry, 4 cross 4 input as a 16 cross 1 vector. And corresponding to this 16 cross 1 vector, I will be overlapping this 4 with 1, 0 with 3, minus 1 with 2, and then I will add here 1, 0. So you can see that 1, 0, minus 1, 0. And then you can see that 2. So 2 is here, overlapped with 4 is overlapping with 0, 3 is overlapping with minus 2. So then 2, 0, minus 2, and then 0. Because this here, there is no role. So second, I am taking as 0. And similarly, you can go to the third row and the fourth row. And so you can see that this is basically a convolution at a single point, at a single location, is nothing but component-wise multiplication of two matrices, component-wise multiplication of two matrices, as is shown here. Is that clear to you? Is that clear to you? Please write yes on the chat box. Okay. Okay, thank you. Thank you. So, keeping this idea, first column of the transposed convolution matrix is just constructed. Your first column of the transposed convolution matrix is just constructed. Similarly, construct the second column, the third column, and the fourth column. We have constructed the first column. In the same way, you can construct the second column, third column, and fourth column. Once the transcon matrix is created, we multiply it with the input of the output of the convolution. And the output will be a 16-dimensional vector. Is that clear to you or not? Yes, so many of you are saying yes. So I assume that this is clear to you. Yes, thank you. So we rearrange it. So transposed convolution is what? First column of the transposed convolution matrix is constructed. We construct second, third, and fourth columns. Once the transconvolution matrix is created, we multiply it with the output of the convolution, and the output will become a 16-dimensional vector. We rearrange it back into a 4 cross 4 array, because ultimately you want to make it a 4 cross 4 array. That is the output of the transposed convolution. So what is transposed convolution, my dear friends? The transposed convolution is not reconstructing the original input matrix or input sample. It is reconstructing the dimension of the input sample. Is that clear? It is reconstructing the dimension of the input sample. So second thing, the third and the fourth. So how do we construct? By just overlapping it here. So The first will be putting here non-zero values, and here it will be all 0. The second time, what I will do second time, I will be putting it here. When I put it here, so here it should be 0, because I'm assuming that my whole convolution filter is of the same size as that of the image. So I will put zeros here, not in the image, but in the convolution. So then my zeros will go like this, right? This will go like this. That is why you can see that I constructed the second, third, and fourth row. Second row, third row, and the fourth row. Then I multiply with this 4 cross 16 by a 4 cross 4 matrix. But this to multiply, I need to convert this matrix 4 cross 4, 2 cross 2 matrix to a 4 cross 1 vector. So that is what I will do. All right. And then, so that is how deconvolution takes place. There can be other upsampling methods, like I told that 4, 3, 2, 1, I apply nearest neighbor. So 4's nearest neighbor is 4 itself. Similarly, 2's nearest neighbor, and 1's nearest neighbor will be this, and so on and so forth. Bilinear interpolation. In case of bilinear interpolation based upsampling, you apply linear interpolation in both the directions. Well, if you have any questions, please feel free in asking. Else we will be moving further. Any questions, participants? There's no question? So there are no questions, so Abhi, go ahead. Right, we go ahead with the discussion. So Anjit Kumar is asking how it is different from GAN, where we generate samples from samples or from a noise vector, right? Or the latent vector. So Anjit, the latent vector that you get in GAN to generate any image or any sample, what is that latent vector? Basically, you can use that latent vector, which is generated through this autoencoder. That is one thing. Second thing, autoencoders are not trained on adversarial training in general, whereas GANs are trained using adversarial training, right? Autoencoders better than VGG16. VGG16 can be used as an autoencoder. VGG16 itself can be used as an autoencoder for encoding part. So there are various autoencoders that can prove to be quite good. Autoencoder, Rishi Kumar M is asking, autoencoder will be applied for X-ray image diagnosis like classification? No, Rajesh Kumar. Autoencoder is used for data representation learning. It's not used for any kind of classification. Later, you can use a classifier on the extracted features of a autoencoder. Any other questions? If there are no further questions, we continue. I told you autoencoders are used. Somebody is asking, that means Rajesh Kumar ji is asking, autoencoders are used for feature extraction. These are different applications, Rajesh. Check. Okay. Now, so now we go to regularization. Now, what is regularization? The idea is to learn meaningful features without altering the code's dimension. That is, if suppose you want the encoded dimension to be 256, we don't want to change the code's dimension. You will say that, okay, if I learn the autoencoder with higher dimension, probably we will be getting better results, which would be true. So why we are doing with a small number of features? But what is interesting here is that the basic idea in autoencoder is to learn the meaningful representation of features without altering the code's dimension, whether it is an overcomplete code or that for a undercomplete code. So regularization, oh, what's happening? I don't know. So let's begin with the concept of regularization. And then I will give you some very interesting applications of autoencoder. So we would like to learn meaningful features without altering the code's dimension, right? The solution can be imposing other constraints on the autoencoder. Let's see. Suppose I told you an example of an overcomplete, one type of overcomplete autoencoder. By overcomplete, you are lifting the samples to a higher dimensional space. If you're lifting the samples to a higher dimensional space, you can see that we can say that 7 is composed of, say, several pieces. One piece is only the bottom, like the top horizontal layer, and another is, say, this diagonal entry, and so on and so forth. So, and then some of them can be redundant as well. So we want to learn our features to be as sparse as possible so that you get flexibility to create any new, to understand or to learn any newly written 7. 7 can be written like this, 7 can be written like this, 7 can be written like this, 7 can be, there are several ways of writing 7. To let the autoencoder understand that this is 7, it has to represent, it has to get it in a truly sparse way. It has to get it represented in a truly sparse way. With the sparse features, you can get more generalization. Like if you did not have enough sparse features, you would have got only this to be understood or recognized as 7. Rest of them, it may fail to understand or recognize. So autoencoder or the sparse representation, sparse feature learning helps us putting variety in 7. It could be 7 like this. It couldn't be anything, right? So sparsely generated autoencoders, what do they do and how do they produce good results? Suppose you have activation function of the jth unit of the autoencoder, right? You have an activation function of the jth unit. See, you have jth unit in the network, and the jth unit will take out some values, and those values are activation values. And let bn j, aj bn be the activation of this specific node on a given input. Is that clear to you? First of all, let an, like this denote the activation of the jth hidden unit. And suppose A, B, and J, X is the activation of this specific node on given input. In that case, let us assume that rho J hat, which is equal to this much, right? Which is nothing but A, J, B, N on Xi, I varying from 1 to M, be the average activation of the hidden layer J over the training set. So you have a jth hidden layer. In that you have M samples. For each of those M samples, I will be taking one value of Xi, and that Xi, whatever is the average activation of hidden unit J over the training set, let us analyze. That can be analyzed. Then we apply the constraints that rho J hat is equal to rho J, where both rho J and rho J hat, so rho here is a sparsity parameter that is typically small. So sparsely regulated autoencoders, the basic idea is to take help of existing knowledge I say that I will be penalizing rho J hat if it deviates from rho. That is a penalty term that is added in the objective function. So they say that let us take an example of this penalty term, KL divergence of rho J hat, if rho J is not behaving the same way as rho. So this is known as the Kullback-Leibler divergence function or the distance function. And KL divergence measures how two different data distributions are, right? Because it gives you the idea like what is commonality between these two data sets and what is their unique or distinct features. So the modified cost function for sparsely regulated autoencoder. Original, remember? Do you remember? We were having a simple formula, x minus x hat, right? Norm square. This was the simple formula, right? And then now I'm putting here before you this formula. Just give me a minute. Sorry, and thanks for your patience. In fact, there is a lot of noise in the surroundings because of some construction activity going on. So I had to move from there to here. All right. So, so what they do that instead of this function, that is the weight, this error function, which is a general error function like here, JWB, because this error function depends on W and B. So x minus x hat, we add here a penalty term, right? So here we need to know rho hat, remember, beforehand, so that we have to, because you have to compute a forward pass on all the training set. So you can see that whenever this error you will be calculating, JWB, This JWB will also be including this. So for this, I must have the value, like I must know what a rho j hat, right? So we have to compute a forward pass on all the training set. Okay, there is yet another kind of very interesting autoencoder that is known as denoising autoencoder. What is denoising autoencoder? The basic idea is to reduce the effect of corruption process, and this corruption process, when the images are communicated from one place to another place through open channels, their corruption is likely to occur, right? And this corruption can lead to noise. And so this is a stochastic process which is applied on any data which is passing through an open channel. Now, so basic idea is to reduce or minimize the effect of this corruption process which happens due to the data traveling through an open channel, or this can be any other reason as well. To encode the input, but not to mimic the identity function, because here, if I mimic the identity function, if you remember what we were doing, we were trying to find out, see, fx was z, this was encoder function, this is encoder, right? And then you had gz, you wanted this to be close to x, that is x hat. So this is a decoder function, right? Decoder function. So if I say that g of, now I put the value of z here, g of f of x, I want that this should be ideally equal to x. That is the basic idea. So x hat tries to mimic or tries to learn the identity function. So the idea here in this case is this, that denoising autoencoder does not learn the identity function. For if it was learning the identity function, this will also be actually containing the noise, which is not expected. So here is a noisy output, noisy input, right? Here is a encoder network. You have a latent representation. Then you have a decoder network, and you have a denoised output. So the question is, the problem is that we want to have a good quality output from a noisy input. That is the basic idea of a denoising autoencoder. So suppose X is an original image, okay, without noise, and X wave is its noisy version, okay. Suppose the output of autoencoder is X hat, suppose. So X hat will be encoder, decoder, X wave, because X wave is the noisy version, right? Instead of trying to mimic the identity function, that is, instead of trying to mimic X wave, which is already a noisy input image, what I will do that instead of trying to mimic the identity function by minimizing the reconstruction loss, the denoising autoencoder will minimize the loss function. It will minimize the loss function. That is the idea. So what I will do, I will add randomly some noise in my image, because we have to train the autoencoder to forget the noise, right? Because we have to train the autoencoder to forget the noise, what I will do, I will add randomly some noise in the input image, say Gaussian additive noise. So this is what we did. This is the original picture, which is here, which is coming like, you know, that there is an original picture, but we do not pass the original picture, but we pass a noisy image, right? So I take some input X, apply in a noise, right? I apply noise. That is what Parimal, sorry, that is what here you can see. Just a minute. Somebody is writing Parimal. No, I'm sorry, I thought that. Okay, so denoising autoencoder, what do? We take a noisy input, right? Instead of original input, and I decode it, right? Encode and decode it, right? And I get an actual good quality image. How do I get? First, what I will do, I will compare. When I am looking at the error function will not be considering the noisy input. It will not consider the noisy input to reconstruct. It will use the original image which is not containing any error. That is how denoising autoencoders were constructed. So here in case of denoising autoencoder, suppose this is the distribution of the data, and you have a lot of data here, all these data. But what you are doing is that you have some corrupted input, and this corrupted input, what I'm doing is that this corrupted input, I will be applying on this corrupted input, I will be this will be passing through the autoencoder, that is encoder and decoder part, and then after it is passed through the decoder part, I will be matching the output not with the noisy input, but with the actual input. That is what I will do. So denoising convolution autoencoders are like with 50 epochs, noise factor as 0.5. They could get, you can get very good accuracy. And these codes are available on Keras IO. Now I give you another example of a stacked autoencoder. To a stacked autoencoder, the idea is to learn the. Now somebody was asking, are autoencoders good for feature extraction? Different types of autoencoders are good for different types of things. Like we just saw a denoising autoencoder. Now it is a stacked autoencoder. What does it do? Stacked autoencoder learns feature extraction for some application. It can be classification application, for example. So we can build a deep supervised classifier where the feature extraction is done by a stacked autoencoder. And then you apply any other mapping, like any other machine learning algorithm like SVM, naive Bayes, any other, or even neural network. So building a stacked autoencoder is done in 2 steps. I seek your attention, please. Step 1, train each autoencoder layer one by one. Each layer will learn to extract features of its input so that it could reconstruct its input. Step 2, once all the layers of autoencoders are trained, then we use the latent representation of the encoder as the input to classify. You must be thinking what I'm telling, just don't worry about it. I'm telling you exactly this thing. That is stacked autoencoder. I get I get a representation of the data in terms of whatever. it can be based on size, reducing the size, or a good quality representation. They apply it to classifier, and then you get the classifier value. You get the good results because you have used a convolution autoencoder specially designed for the purpose to extract features from a given data set. So I seek your attention. Now, if your image is going like this, F1x, Z1, Now, so this is your encoder, and this is your decoder. So you can see that X passes through encoder, it gives you Z1. Z1 passes through decoder, it gives you X hat. Then what is happening? See what is happening. Here, in case of a stacked autoencoder, whatever is learned by this, it is completely done, that is saved. Now I go to the second layer. When I go to the second layer, I forget about this layer. This is all kept secluded. I go to the second layer. Here, you can see that once I get this Z1, this Z1 is fed to the encoder, to the second layer of the encoder. Are you getting my point? See, I have to have a first layer. What I will do, I will consider like an input layer and output layer of this first layer, right? Suppose the output layer is, say, you have whatever you want to call it. So this is my X, this is my Z1, and this is my G1, Z1, G1, right? This is my G1. So this is my F1, and this is my G1. So the idea is that I train this single hidden layer network very well so that it is able to extract the data. Then once this is done, I go to add the total number of, I go to add another layer here, as you can see. And I will keep repeating the same process for each added layer. For each layer, I will treat this as an independent single hidden layer which learns to replicate itself. So in a stacked autoencoder, you can have this arrangement also, where you are training layer 1, layer 2, and when the training is over, you can give the amount, you can give the whatever was asked by her regarding some kind of, I mean, whatever is asked, whatever is the need of the application. It can be a classifier problem, or it can be any other kind of problem. But stacked autoencoders are used for classification only. Now I come to some applications. So UNet architecture was one of the most celebrated architecture, which has been used for segmentation, of biomedical images especially, and using very few images as compared to other convolution autoencoder, it is able to reconstruct the input sample very clear, I mean, in a very good way, right? This is, so there are some questions. I will take some questions at the end. So applications in image segmentation, this is another encoder decoder architecture. Although we do not call it like exactly the autoencoder, it is an encoder decoder architecture which is there, right? So this was introduced in 2019. You can see that there are two parallel encoder decoder architecture, and this is the encoder which uses some part of it, some part of the VGG as well, and then it uses the decoder architecture. A parallel CNN layer is also there, which that also uses a VGG type of VGG layers initially, and then it uses an encoder and decoder architecture. So both the networks, their layers are, the output of their layers are combined, and you then find out what is the feature map for this type of input, which is given here. Now, so this is a, I'm sorry. So this is a joint work with of my student with Professor Preeti Khanna, and we are also, I mean, three of us are doing, where what we do, this is the original image, this is the ground truth. Now you can see this is not purely unsupervised. It is a supervised learning method. Here you have an original image, the ground truth. You have smoke data set where you are identifying smoke. So what we do, we start with the data pre-processing. We split the data into two parts, that is train and test data. Then training data, we are sending to two parallel architectures. These are some special kind of architectures that they're using here. I will not go into details of that. So, but it uses a residual encoder, residual network. It reuses a residual blocks, and then we apply certain kind of attention. We fuse the shallower and deeper path, and then we find out the segmentation. So results appear to be quite interesting. As you can see, with as compared to others, on this benchmark data set 1, 2, and 3, it is proved that the method is able to produce better results than other results. If I look at the qualitative results, you can see that this is the these are the original ground truth. These are the images. These are the ground truth. So ground truth, you can see, my dear students, is labeled like this. Shubhangi, I will ask her. Shubhangi, are you there? Are you going to tell her what tools can be used for labeling the data?
Image J software is available, as well as Label Me is also online software, and Image J is a software that is based on Java that can be downloaded, and it can segment the ground truth.
Okay, thank you. So you can see that these are different people who have defined, who have proposed segmentation models. And in the context, some of them are particularly in the context of smoke segmentation. And Shubhangi is working on identification of fire at an early stage, for which smoke identification is important. So she's working on these problems, and she has come out with some good results. This is what we have said, and you can see that why this architecture that we showed, I just showed, is so important, because it also not only that it looks at the smoke in the context of in the context of ground truth, but it also is able to find out smoke in challenging condition. Like if you have the background color same, then also it is able to produce well. If you have foggy environment, you know that in satellite images or in any other image, if you have a foggy environment, whether smoke is present or not, finding out becomes difficult. Although the method is not doing very well in this case of fog, but this is one method, this is one area where a lot of research is going on, that identifying objects, in particular smoke, in hazy environment, in foggy environment. In case of low illumination also, it is showing good results, except on data set 1. And like background is the same here. Now there's another important study that our image and vision group at IIIT DM Jabalpur is doing, and that is a study of loss function. So what loss function will be useful for convolution autoencoder? I will come back to you, don't worry about it. So this is the structure of the convolutional autoencoder they have used. So this is a joint work, I forgot to write. This is a joint work with, so this is actually work of Nishant Khare, one of my student. Purnima, you know her already. P. Khanna and me. So here it comprises of total 8 blocks. So we studied these different loss functions: MSE, mean square error, binary cross entropy loss, and then we used by taking the Laplacian loss function, where L denotes Laplacian of the image. And then we use several different types of loss functions, including Sobel loss function and the focal loss, the last one. And then we tried finding out, you must be thinking why we were using loss function. We were trying to figure out which loss functions are suitable for what kind of input images. So if we take data sets, if we took data sets of different types, like handmade digital sketches, medical images, natural images, different types of images. And you can see that some of them are grayscale. So this is the one that I showed you. So Nishant worked out on this, and qualitative results also. You can see that if I take this MSE loss, this is the original image. If I take the MSE loss, with respect to other loss function, it is not able to produce good results. So MSE loss is giving you good in this case. If I consider like a grayscale image like this, then some of the like Laplacian or other loss functions can give rise to some loss of information. So my student Nishant came out with the conclusion that the MSE loss function outperforms on data sets with low dimension and large number of training samples. And CAE, that is convolution autoencoder, can adapt well with BC loss function on high dimensional images, even with a very relatively small number of training samples. So there are so many different types of autoencoders which are there, and we have found out that these encoders prove to be quite autoencoders prove to be quite useful. So with this, my discussion on autoencoder stops here. And if you have any questions, please feel free in asking. Then maybe I will quickly tell you something about object detection. I'm going back to number of stacked layers will depend on the complexity level of features to be learned. Ashwin Yadav, yes, mostly, yes. But even very small autoencoders like 3 to 5 layers, 8 layers, 10 layers do very well. Can we use autoencoder for thresholding images? Why you would do it for When you can do it with simpler methods, Dr. Arshad Iqbal. Classification, it is not used, Rajesh, as I told you. Autoencoder can be used for feature extraction. Yes, I told you. A number of stack will depend, yes. And then can you please repeat the name of tools used for image labeling? She will tell you in the lab, Amit Kumar Pandey. Please write the name of tools. Many people write. Image J, she's writing here. Can we segment without ground truth? Neha Rathod, that will be unsupervised learning. Yes, we can. Can we, yeah. Without ground truth, so she is writing, Shubhangi, without ground truth, you can use image processing tools like, no, Shubhangi, she's asking about without ground truth, can we train the autoencoder? Yes, you can, that will be unsupervised learning. Can we use autoencoder for thresholding? That I've already answered. Amit, I just told you the example. Isn't it a semantic segmentation? Right? It is a semantic segmentation. If you have any questions, please feel free in asking. Else I would like to move to another topic. Because we are doing a smoke segmentation, we are not doing, Amit is asking, that was image segmentation. Is it same? So you can have semantic segmentation, you can have instance segmentation. In case of instance segmentation, you will be actually segregating each different instance of the smoke occurring in the sky or wherever. No question. Shall we go ahead with a simple, quick downsampling? Max pooling is a downsampling, Kalpana Sharma. Max pooling is a downsampling. She's asking, is there no downsampling in autoencoder? Answer is no. I mean, yes, there can be downsampling. Okay. So there are no questions. I would like to quickly take you to object detection, because I came to know the other day that unfortunately object detection could not be covered. So I will take you to object detection then. Just give me a minute.